Okay, welcome back. Last we learned how to calculate gravitational force with Newton's law of universal gravitation, gmm over r squared. But if we combine this with this expression, which we used last semester, we see that the force of gravity on Earth, I'm sorry, that's supposed to be a g, where g is 9.8, we simply multiplied 9.8 by our mass to get the weight, or the gravitational attraction to the Earth. Well, if that's true, then this mass, if this is the mass of the object attracted to Earth, maybe I call that the second mass, then this stuff must equal this guy. So I get a new expression. Little g, gravitational acceleration, is gm over r squared. Almost the same, but without the mass of the object being attracted. So, this gives us a universal expression. We know that if we put the mass of Earth and the radius of Earth and use our universal constant, this will equal 9.8. But if I go to a different planet, or if I'm someplace near Earth but not on the surface of Earth, I can calculate the acceleration due to gravity to be something other than 9.8. So let's try this with Jupiter. Let's pretend that we could stand on Jupiter, despite the fact that it is a gas giant. And we wanted to know the acceleration due to gravity on Jupiter. If you dropped a ball on Jupiter, how fast would it accelerate? So we're going to need the mass of Jupiter, and we're going to need the radius of Jupiter. Now this radius is not the distance from Jupiter to the Sun. It's not the radius of Jupiter's orbit. This is the radius of Jupiter, how far you would be from Jupiter if you were standing on its surface. Or rather, how far from its core you would be, or from its center. So if I look on the chart that came with our packet, I see that the mass of Jupiter is written as 318. Remember, that's not in kilograms. That's 318 Earth masses. So if I'm finding this for Jupiter, 318 Earths, and its radius is not written in our diagram. Rather, we have a diameter of 143,000 kilometers. Now, just like finding force, we needed mass in kilograms and distance or radius in meters. Once again, we want this in kilograms and meters. So if I'm going to solve this for Jupiter, g on Jupiter, big G is always 6.67 times 10 to the negative 11th. Now, the mass of Jupiter is going to be 318 times the mass of Earth, 5.98 times 10 to the 24th. So these two together, the product of these two, gives us the mass of Jupiter in kilograms. Now, the radius of Jupiter. I need to do two things to this number. I need to take that value, 143,000, and I don't want the diameter, I want the radius. So I need half of 143,000, which is going to be 71,500. And note it, so that's the radius in kilometers. But I don't want it in kilometers, I want it in meters. So I could do this a couple ways. I could just add 3 zeros because there are 1,000 meters in a kilometer. Or I could have written this as 7.15 times 10 to the 7 meters. Either way is perfectly fine. Now, what does that equal? Once again, I'll show you on the calculator. Putting my numbers in using E, 6.67, E, negative 11, times 318, times 5.98 E, 24, divided by my denominator, squared. I'm going to do 7.15 E, 7, and I'm going to square it. And I get a number. This is actually slightly different than the value in the chart that was included. I'm not sure if that's because Jupiter is not perfectly spherical, so its equatorial radius is different from its average radius or something. But either way, we get a number 24.8 meters per second squared. So if you were on Jupiter somehow, standing on a scale, your weight would not be mass times 9.8. Your weight, or the force of gravity on you, would be mass times 24.8. Notice this is more than twice the 9.8 on Earth. So you would weigh more than twice as much on Jupiter. Also, if you dropped a ball on Jupiter, you would see it accelerate more than twice the rate. It would gain 24.8 meters per second every second while falling towards Jupiter. Why would this ever matter for us? Well, let's say we want to send a satellite to orbit Jupiter to monitor something for some reason. When we send a satellite to orbit Jupiter, some satellite cruising around, we could find the height or the radius of that satellite's orbit, and we would need to know this acceleration due to gravity to know what velocity to give our satellite so that it stays in stable orbit around Jupiter.